Is the screen visible?
Yes, sir.
Good. Okay, so in this whole course, as we go along, we have seen two types of, in broad, we have seen two types of learning. So one we call it as supervised learning, and the other we call it as an unsupervised learning. So in supervised learning, so in the supervised learning setup, there is always a teacher, right? Because you are given an example x1 and also what will be the correct output for that example. Similarly, you are given such training examples up to xn and what is the correct output. So which means that there is always a teacher to help you in every sense. In other words, we have also seen something called an unsupervised learning. So there is no teacher, but you need to find out certain kind of patterns in order to cluster or group something. So there I do not provide you anything here. And so on up to xn, I have n points, but I do not provide you anything in the as an outcome to read above. So you can see here you have a feedback which you may say it is immediate, right? Because for every input you know what is the correct level or the output, and you have a trainer which gives you the immediate feedback. Whereas here you can see there is no feedback at all about the inputs or the data points that is given to you. So in this week, with today and tomorrow, which we will try to look into, is a third category of learning, intermixing these two, where the training data in our hand is a mixture of in between these. That means we do not have an immediate feedback, and we are not, it is not the case that we have no feedback at all. So our training data here consists of certain inputs, and there would be the feedback that we get from this is what we call as a delayed feedback. For example, you may take an example of game playing like chess. So it's a move between two players, and you just go on playing a move, and the board position keeps on changing. But after you get to know about the win and loss, then you can level it that +1 is for win and -1 is for loss and maybe 0 for draw. So these are the final outcome which is delayed because the way you play and shuffle the game board positions until you reach a win or a loss or a draw, you do not get a +1 or a -1 or a 0 outcome. So that's what we mean by a feedback to be delayed. And how can we learn such kind of a behavior where we need to we need to devise a mechanism or a policy by which if we push ourselves through that policy, our reward in so-called sense or our feedback will be maximized. So this is the field we call it as a reinforcement learning. So the word reinforcement is somewhat depicts this delayed feedback because it gets reinforced into different positions of the game, and therefore you try to accumulate and gather a cumulative feedback. To maximize your feedback, you get a better and better policy. We will see all these factors. So in a typical setup, as you see that this reinforcement learning is obviously dictated by a sequence of steps. And that sequence of steps meaning that I will follow this sequence of steps and ultimately I will reach some goal where the outcome I may get as +1 or -1, so as to say. So it will follow a sequence of steps, and this in machine learning terms sometimes we call it as a policy, that I need to devise a policy in order to make sure that I reach from a starting position to the goal. Now, where is the setup in which we encounter such kind of a problem? Let us try to see the generic setup where this chess belongs to. You may think of this model as that an agent is acting somewhere in an environment. Suppose this is the environment and your program is the agent. That is, suppose you are playing, let's say, white in chess. And then what you see that at a board position in the chess, you sense that board position, right? Which means you sense a state, which is a board position. And depending on that, you make your next move, which we also call as an action. So that is the setup of the game or maybe the environment. Now you can see if you sense a state and you make a move, you do not get immediately the feedback that it's the best move, right? After a long amount of play, you get to know whether you win, loss, or draw. How was your this move and how was your that move? Maybe there are certain board configurations where you may take more pieces than the other, so your position is better, so as to say. So that means in between, after getting a state or a board configuration, when you place your one of your moves, then immediately you also get a reward, right, from looking at the board position. So therefore, you can see that to formalize such kind of a setup, we have a set of environment states through which environments move on. Let's say from S1, environment moves to S2, then environment moves to S3. In chess, these are the board configurations. Sensing those states, you need to make a move. So in S1, you made a move A1, and hence the board configuration for the environment goes to S2. And you collect some reward R1. If for, let's say, very crude manner, if we say that the reward will be whether we win, loss, or draw, then intermediately in the chessboard, we will make the reward as 0 until we reach a final configuration where we checkmate others, or maybe a draw configuration, or maybe a loss configuration. So the basic setup of the game, as you can see, it follows a Markov decision process. Why? Because if you try to remember the rules of the Markov decision process is the probability of the state t happening is only dependent on the previous state and the actions at t minus 1. Right? Because I only care about the board position. I only care about my next move to reach the next state in the environment. Similarly, if you also see that the probability that you get a reward from that board position is also dependent on the previous state and the immediate action that you have taken. So this is the inherent assumption of in this reinforcement learning setup that we make, which is our MDP assumption, that is, it's a Markov decision process. So under this setup, what is our challenge? Our challenge is to learn a policy so that we could guide the agent to reach its goal, which means I want to learn a policy. I would say it's a pi, which what is my policy that given a state configuration, I will provide an action. That is my policy, that when I start, I move my pawn to e4 from the board position e4 to e2 to e4. Then the opponent plays the pawn from e7 to e5. So these are my actions that I do. So with this sequence of actions, I need to reach a goal. Therefore, I want to learn this so as to maximize my reward, so as to reach the desired outcome. This is the problem that we are trying to solve. Any questions till this point? Right. Now, look at this. We are trying to learn a function. Now, look at the colloquial supervised learning that we have done so far. Right? In supervised learning also, we are trying to learn from the attribute level of function. So ultimately in supervised learning, this was our learning outcome because we want to learn a hypothesis that would mimic my function. Here also you see in the reinforcement learning setup, we are trying to learn a function pi as well. However, the difference with the supervised learning is you are given the training example x1, y1 up to xn, yn, which is specifically for the input. You are given the correct output for the other input. You are given the correct output and so on. This is your training examples. In reinforcement learning, it would be similar if we are given a state with an action as my training, right? If we are given such kind of a sequence as your training, and now I say to learn a policy with respect to these training data, the problem is same as supervised learning problem. However, what we are given is instead of this, we are given a reward here. Instead of this, we are given a reward here. Everywhere where we have a state, we are given an intermediate reward at state I instead of the direct outcome or the final goal that to be attained. So this is the training example for reinforcement learning. This is the training example for supervised learning. So that's the primary difference. So the algorithm in supervised learning will not directly be applied to learn for a reinforcement learning such kind of a action sequence of setups. Now, you also might think in such a way that why such is the case, because even if this a simple game like tic-tac-toe, chess is a much vast game, you can see that a trainer cannot provide all possible combinations of different training examples so as to say to learn the variations in the policy. So if I have to apply supervised learning kind of an algorithm, I need to know which state, which action is the best. And I need to have a huge amount of such training examples, which is often not feasible. Consider chess. Can you provide a huge number of training example considering all possible possibilities or at least reflecting all possibilities? It cannot be possible. Can never be possible. So therefore, in a way, this reward are your intermediate goal that kind of acts as a guidepost to reach the overall goal. In life or in general problem solving, we often sometimes follow such kind of a step because one of the reasons is that we cannot foresee all the variations. The other reason, the environment, these are Markov decision process because these are hidden Markov models. You do not see these states moving. You see by an observation, that is your move, and this observation, the reward that you get, whether you do good or bad. Okay, your queen gets sacrificed, you are doing bad. You capture someone's rook, you are doing good. Right? So it's not always that you foresee this. If you can foresee all of the states and all the transitions, then it's just a search problem to reach the goal, right? But here the problem is in manifold. You cannot foresee all variations. You cannot foresee the intermediate environment sometimes where the environment is moving. In chess, it's a deterministic thing. In backgammon, sometimes your action is followed by a dice throw and it's random, which of the action is giving which of the state as an outcome. So therefore, reinforcement learning itself poses certain challenges, which makes the algorithm of reinforcement learning to be difficult to realize. So one of the challenges is, as I mentioned, the outcome of action is uncertain. You consider the example of backgammon. Backgammon is a game where you have to make a move followed by a dice roll. So then you need to throw a dice, and then depending on the outcome of a dice, you can get into a different set of environment states. Sensing that reward, again you have to move. This is the backgammon game. So you can see that outcome of an action, even if you have moved and you thought that it's the best option that I could do, but there is a non-determinism after that. The second thing that makes it also challenging is you do not have a perfect sense of the environment. Sometimes your environment, you only see it through rewards, right? You do not have any sense about where the environment is moving. Are there any noises in the environment? So all of these act as play, noises, non-determinisms in the environment, all these acts and make the problem too difficult for solving. The third thing that we also see as a challenge in this reinforcement learning setup is that your reward is delayed, right? I mean, you play a game, I mean, you do not know whether this move, I mean, no piece get captured. How do you know this board position is a little bit better than the other? Sometimes it's a flat outcome after one move. So you do not know the reward, I mean, whether this leads to me the goal or not. And sometimes in the game of backgammon and many other situations where we do with the control theory, the reward is stochastic as well.
Sir, can you hear me?
Yes.
Sir, can you go on the previous page once? Yes, sir. Sir, actually, the probability you wrote for the reward and state, when we are observing, like, we are trying to maximize the probability and we will choose that action, right? Like, which one is giving the highest reward? Or
Not necessarily. That's a greedy choice that often is not how algorithmically we try to do. We will try
so,
to have a dynamic programming kind of an algorithm. You are doing a greedy, right? At the present board configuration, what is the best action is your greedy choice. That's not necessarily what we do when we try
so,
to solve and learn a policy.
so here the intuition behind these two probabilities, like we are trying to maximize these two, right?
No. I am saying it's the setup of the reinforcement learning problem. The setup is that it's a Markov decision process because your action, the next state, is only governed by the previous states and your present action. And the reward is only governed by the previous states and the action you make. That's it. It is not dependent on the prior state than the previous one.
Okay.
Okay, that's the only assumption in this reinforcement learning setup we make. And indeed, it's a valid assumption because wherever you land up in, the history doesn't matter much. I mean, I will also show maybe in the tomorrow's class a little bit variant where instead of only seeing this, we need to see a little bit of history in a window to get a move. Okay.
So the actual intuition here is like it is dynamic.
Yes.
Like
It will be a dynamic. I mean, gradually I will come today in the algorithm.
okay.
Okay. Just let me put down the challenges, then I will formalize this more, a little bit more. So you can see that the reward is delayed and it could be stochastic, and often the environmental action is also unknown. I mean, it may be noisy non-determinism is one aspect, but you do not know what the environment reacts to it, right? You do not know the environment properly. And environment continue to change. You may be in a changing setup of an environment that the environment, the model of the environment continue to change. And most importantly, this is a very interesting point here, that how much do you train, right? Since we are learning, so this question is very interesting that see, since we are learning, so how do you make a machine to learn chess game? We will give certain board configurations and certain dynamism of the play leading to some goals, some rewards. That's my training example. It will be certain sets of moves followed by a delayed reward. So how many of them will you do? How many of them will you do to make sure that your reinforcement learning agent or the machine has learned enough and can play now for its own with anyone else? So with these makes the problem challenging, that when to converge and say I have learned enough. So again, as Urvashi was being impatient about the formal setup, let us again try to figure out that what is happening here as in terms of a formal setup. So let us write the task here. We are trying to find a policy with respect to each state. We try to reach each a particular agent. Therefore, you can see that at state 0, what does it mean? That at state 0 of the environment, I can have different actions. I can do A0, I can do A01. This is A00, A01, A02, and I can reach to some state S1. I can reach to some state S1 dash. I can reach to some state S1 double dash, and so on. I can choose another action and go to this. Now, what does a policy mean? A policy means a pathway, right? I mean, which of the actions do you select one after another so as to reach your goal? That is what the policy is all about. Now, since you can see my reward is delayed, right? So somehow I need to embed the reward through the path of the policy that I select, right? So this orange color path is a policy, and I need to see that from state S0, if I take an action A0, how do I evaluate that through this policy pi? If I take an action A0, what is my cumulative reward? It means that suppose I am at a state S. Let's say I am at a state S, and I choose a policy pi. So we call it as sometimes as a value function. It is nothing but it's just a cumulative reward to compute, which is what I will do. The immediate reward that I get, if I choose this action, immediately I get a reward R0, let's say. So the immediate reward I get at state, say I am state it's SI, immediate reward I get at state SI choosing the policy pi, which is A0 followed by A1. This is my policy. Okay, followed by AN. So here immediate reward plus a little bit discount on the reward for the next state, plus a more discount for the next state, and so on. What does it mean? That it means that nearer the goal or nearer the higher reward you have, the value function of a state will be more. Which indeed makes sense, because if you see, I'm giving it a common kind of a notation for this. So if you see that it makes sense, because I mean, we are more bothered about the current outcome rather than what will happen in the future. For example, it also see, suppose you are driving a car and this is your lane. Now your car is moving this way. Suppose, so as you can see, the state of the car is x, y coordinate, but where it is in, and also you can say the angle, I mean angle of the straight line, the theta. So the state of the car you can visualize as x, y, theta. Now suppose you deviate the lane. So you have to apply an action. You can apply this, you can apply this, you can apply this straight. These are all your actions, or you can apply drastically this. Depending on the speed, the action has a reward. Drastically, this word may collide here. Little bit small, this word may come inside the lane very fast. This could be very slow. It also depends who is there in front of you, right? So therefore, I mean, what you want to believe, I mean, what you want to do, you will try to make rewards of according next states accordingly. So immediate a question comes that how to design such rewards, right? And this is a very pertinent question. I will just not answer this question right now, but suppose, for example, I can design my rewards from a state if I choose an action. Then what would be my goal? My goal would be finally to devise a policy which is optimum from every state. By optimum, I mean that any action I choose, so RSA is the reward in that state, plus gamma is my discount. This V star is the value at the next state if I go to next state with the A transition. And if I take, so if I go to the next state with the A transition is my this. So let us understand it more, that what does we mean by an optimum policy. It means that for every state, see, it's kind of a recursive definition with respect to my value function. So what I want to mean is that I want to maximize. So I am at a state S. There are many actions. There is action A, there is action B, there is action C. So here my value function, the V star at this particular state, suppose this state is S1, this state is S2, this state is S3, and I am at S. So this state has a value function. This state has another value function. This state has another value function. Now I will get discounted reward. There are paths from this state, there are paths from this state, there are paths from this state. I will get a discounted reward with this state reward plus gamma into this state reward. I want to maximize which path will lead me to the most successful in terms of the cumulative reward that I gather. That would be my strategy. I mean, in a common sense, that should be my strategy, obviously, right? I mean, you are at a state, you need to move to that state which can maximize your reward in the future from that state. That's what this optimal policy formula is. Okay. So we also, yeah, I think there is a question.
Yes, sir. I have a question. Sir,
Yeah.
you were saying that the process is Markov decision process, but while you're designing V by SI, we are writing I plus gamma of RI means RI plus 1. So that means
Now
it is
gamma is a discount. I mean, that's in my hand. So it's a less than 1 greater than equal to 0 value. Suppose it is 0, then what will happen? It is 0 means you are only getting a reward for the present state. You are not encountering any of the future to have your decision.
yes.
Right? If it is
Yes.
1, I mean, I'm saying it less than 1. If it is 1, what it happens? It kind of an average, right? Till the end. Because you are adding all the rewards. It is getting averaged kind of. Right?
Yes, sir.
Yeah. So let me also give another example, and which is very naive one, and every textbook has this because it's very easy to explain the concept over the example. Suppose I have a robot and this is my goal state. Now the robot has to just reach here. Wherever I start, the robot has to reach here. And if I take this move, the robot gets 100 reward. If I take this move, the robot gets 100 reward. If it is in the goal, there is nowhere to move, it has reached. All the other moves that you take, the rewards are 0. Because you do not know whether you are reaching towards goal or not in a practical environment. Now, what will be my value function so as to say that, see, the value function, if you look at the value function now, the value function obviously is the reward at the present state plus gamma into reward at the next state and so on, and which can be obviously for an optimal policy. So the value function for this in state S, I write it as V star S because it's just selecting the best move to reach the goal. So what will be my V star S for each of the state which robot reaches? That this is state S1, this is state S2, this is state S3, this is state S4, this is state S5. So you can see that if I am here, what will be my value function at state S2? The optimal value function at state S2 is I can take this action. So there are also actions like this, 0, 0. I can take this action and reach goal. I can take this action with a 0 reward. I can take back with a 0 reward. So if you try to compute it, the current reward at here may be 0 plus, let's say the gamma is 0.9 into maximum among where you can reach. So 0 this side, 0 this side, 100 this side. So this is the maximum between 0, 0 and 100. This 3-way I can do. I am taking a maximum of that. So therefore, this is 90. So my value function here is 90. Coming back to here. So suppose here also you will be seeing 90 because these two blocks are the same in terms of the computation. Now what about here? See, the value function is a recursive definition, right? It's a recursive definition that taking action you reach to somewhere where the value function is maximum. So if you take this
Here
action
it
also, I
should be
get
0.
90. If you, excuse me.
Okay, sir, got it. It will be 0 plus
Yeah, please go ahead. Go ahead. Please go ahead. It will be 0 plus.
0 plus 0.9
Yes.
multiplied with 90, maximum of 90 and 90 and yeah, 0.
Yes.
Actually, in braces it will become yeah, obviously, yeah, it will be
Right. So
yes.
actually, I mean, as per the colloquial sense, I made a small mistake. Actually, this will be 100 in a sense because we only go with the moves. So see, your reward is basically state action gives you a reward. So the in this state, if I take this action, reward is 100. So this is not 0. This is 100. I mean, I do not need this one, right? Because my reward is in a state. I take a action, I get a reward, and I reach to state S dash. So in this state, if I take this action, my reward is immediate reward is 100. So the other actions immediate reward is 0. So therefore, the maximum is this side and immediate reward is 100. So in fact, I made a mistake. This is 100. So all of these should be 100. Okay. This one,
That will be
as
90.
Urvashi said, it's absolutely what Urvashi said. It's 0.9 into the best move that you can make to get the value function maximum. This is 90. Now somebody can compute this state S1. What will be the value of S1 in the optimal move?
That will also be
This is 90. You know, this is 100. This is 90. This is 100. So from here, you see, if you go this side, it is 0 reward. If you go this side, it is 100, right?
that will be 90 only.
So in immediate reward is 0 plus 0.9 is your discount plus 100 is your this state reward. So it is 90. Now what will be V star S3?
That will
This
be
one.
81.
Why? Because immediate reward, if you have any side move is 0. Discount factor is 0.9. Now when you get a discount and then you move a state which has
9.
90.
Deepak, can you mute yourself?
Yeah, I mean, Deepak, do you have any other suggestions? I mean, everybody, are you understanding how you are calculating this one, the value
Yeah.
function? Is there any doubt? Please, you can please ask. Now, see what it means is that let me only write the value function that I got. Then it is a clear indication that where. So this is our goal. Value function here is 100. Here is 100. Here we got 90. Here we got 90. Here we got 81. Now, what will be my policy? My policy would be the reward in the value function and then immediately moving where to go, where I can go best. So my policy would be that I can go this, I can go this, I can reach this. Or there will be an alternate policy. This is also an alternate policy, right? Or I can go this way, I can go this way, I can go this way. See, among the next neighbor that I can reach, anywhere 90 is my best option. From here, this 100 is also my best, this 100 is also my best. So to note here is that there could be alternative best policies, right? If we do these value iterations. Agreed till this point.
Yes, sir.
Right?
Sir,
Yeah.
there
Yeah,
is also a possibility like from 81 it goes to 90 following the orange arrowhead, then
yes.
from 90 to 100, then
Yes.
to 90 which is below
No,
100.
no. It will not go there, na? Because see, 100. Why should it go to a state which is lesser?
Okay, yes, sir.
Right?
Yes, sir.
But
Yes, sir.
one silent thing I do not mention here is that see here to lay down a best policy, you need to know all this. you need to know all this. Right? Because you computed all possible best value functions in each state. Right? Which is infeasible because in a large state space, can you compute everything or can you know everything? It is impossible.
But sir, as you were saying, it is dynamic problem, so there must be some overlapping problem, and
No,
we can.
now see the challenge. See the challenge here. Effectively, how you computed this? You computed this in a kind of, let me use another color, breadth first manner. First, you computed in a breadth first way the immediate frontier of this. Then, in a breadth first way, you can compute this. Then, in a breadth first way, you can compute this cell, right?
Yes, sir.
So, if you have in this is a very small state space of the environment. I mean, you can easily see considering chess. Can you do in chess from a goal state in a breadth first manner? Can you search through the space and can dictate every value function? You never can. There comes the learning now. As you just try to take the analogy from maximum likelihood estimation. When you cannot have the whole joint distribution table, what did you done? You have just estimated it with respect to the frequencies of it. Here also, it's a different kind of a learning. Not we will estimate just like in MLE, but it's a problem in a huge state space. In a huge state space, and suppose something may be obstacle to, right, in a huge state space. So here is a goal. I leave you here. I mean, where should you go and reach it? You cannot just go on computing the value functions and do it. So you need to be smart about it. Number one, and the second thing, going to be smart about it is also you have another weapon in your hand, that is a set of examples I give you, and my examples are of the form that I give you a cell and a reward followed by a cell and a reward. This is one epoch of my example. Suppose I give you this example, then I may give you this kind of a training example, then I may give you this kind of a training example, right? In chess, I give you a game, a full game, 20 full games. All full games will follow a different paths to the goal or maybe somewhere. Let's say 70 intermediate board configuration and play. So what essentially I have given to you, are you understanding? I am given to you a state and a set of moves, another state and a set of moves. Depending on that, I need to learn now. This is the learning problem. I mean, this you need to be very clear about. It's not a search problem anymore. It's a learning problem due to the inherent nature of the state space is huge, due to the uncertainty of the model that you will see in the next class, that your actions in the environment may have a probability of going to certain state, not a deterministic flow. So it is not always an MDP. It sometimes is a partially observable MDP. And also it's an MDP where actions are non-deterministic in producing outcomes. Okay, we will see all this in the next class. But for today, right now, that if we could not compute all this, what is the mechanism to learn from examples? Right? So here is one, which we call Q learning. It's the most popular reinforcement learning paradigm that has been ever evolved. So what I will do, let me start with the example. I have this, I have this, I have this, I have this, this. Well, I do not need this one because if I reach a goal state, it's self-looping. So I complete it. Now what this Q learning does is that, remember our function pi star s. It is argmax of the action, which has an immediate reward on A, plus a discounted reward that we would like to see on the next transitions that we make over this. Now, often, I mean, just to make completeness, I do not believe in jargons, but I need to give it because otherwise from book when you read, it is called a Bellman equation. Because that's the same Bellman-Ford, that shortest path algorithm that Bellman has invented this. Now, in a deterministic setup, this you can easily visualize in terms of multiple linear algebra kind of a multiple equation and multiple unknown. Because if I am in state S1, S2, S3, S4, S5, you can see that I write the value function at S1 in terms of the reward at S1 plus gamma into value function of S2 plus gamma square into the value function, I mean, of G, the goal state. This is one equation I can take. I can also take, so if this is a policy to make it. So for each of them, value function of S2, similarly, you could have another equation. So you can see the value function metric, if you write the value function metric, this is VS1 up to VS5, you can easily see it's a metric of rewards in plus gamma into the value function metric again, right? You can see it in terms of this linear equation solver as we solve the value iteration. Yes or no? How do we solve this value iteration? We formulated equations. There are those many equations, those and the same number of unknowns. We solved it, right? Yes or no?
Yes, sir.
Yes, sir.
Did you get it in this setup? How are we solving this? We have the equations in terms of this, right? And those many equations we have, those many unknowns we have. So these are my unknowns. So we know R, we know gamma. Gamma is our constant. R we know. So if we know all the R's, then these are the linear algebra equation solving that we are only doing. However, let us try to model this problem in terms of why the Q-learning comes, because people try to model this in terms of a function which is called QSA, which says that what is my best action A at state S. If somebody could say you this, then your pi star, the optimal policy A, is nothing, but you are just maximizing with respect to A, the function at S. So just try to imagine somebody provides you this. Now your optimal policy would be what? That at each state somebody provides me what is the best action at that state among all the values or the actions that you can take. Which Q value is the most? I will go there. Which Q value is the most? I will go there. Right? Now, how do we compute this in terms of iteratively, or what does this bring in? I mean, just changing the VS name to this, what important thing does it bring in? Now see, what I will try to do here is that I will try to iterate from a board which has no values initially. How do I iterate? So initially, I will set up every Q value to 0. Every Q value to 0. Remember, you have these actions. All these are 0 except this one. Let me draw which is non-zero in a different color, except this one. This one has 100 and this one has 100. So initially, I have all the Q values. I just go and do a 0 for them. Now what you do is that when you are at a particular state, suppose at any intermediate iteration, let me draw the intermediate iteration board in front of you. So at any intermediate iteration, suppose I am in such kind of a scenario where my robot is here, and let's say I computed this as 72, this as 63, this as 81, and this as 100. Now, when I make a move of the robot to this place, how do I update the Q value? So I would update the Q value of that particular state with a right move that I make of the robot with the current reward plus gamma into max of all the transitions and the Q value that is there in the new state that I reach. Suppose this is state S1, this is state S2. I do a S1 and move a right, then I go to S2 with all the A dash transitions we have in this. So this is one transition, this is one transition, this is one transition. This is 100, this is 63, this is 81. So that means the max will be 100 and the reward in this state was 0. So 0 plus 0.9 into 100, which is 90. That means then what I do, I get an update of the Q value function from this state with the right move to 90, which means I change this to 90. So let me repeat again from the initial. We are at 0. You start at any arbitrary state. Let's say I start from here. How do I update? Suppose I update the Q value of this state. Let's say star is the state name as I indicated. With a right move if I make, that is this move, what will be the value here? I update where I go. From there, this move is 100. This side move is 0. This side move is 100. So the max among them is 100. So this.
But sir, right now it is 0. Like.
No, zero is the initial key value or the initial reward of it.
So we should have computed that one first, no? Otherwise, the below G.
Okay, I'm naming it. No, see, here is the beauty that unlike earlier, when you have to go for a fixed breadth first such kind of a strategy, then you compute this, then this, and then this. Now here, your move will dictate what to compute. And when you move, the previous Q value get updated.
But so when we are moving,
you are moving in the right. You are moving in the right. So your Q value for this state for move right is updated.
But simultaneously S5 will also be updated, right?
No. S4, not S5. S4 will be updated. That's what I'm saying. When you are moving right, the position from where you are moving will be updated.
But so we don't even know the.
No, see, the thing that you are saying, suppose you are here, right? Then it is 0. Because if I also move here, this is 0. Okay?
Yes, sir.
Then this is 0. But if sorry, I'm sorry, here. Suppose I am here. If you move any of the places, this is 0 because all the outcoming edges has 0 action values. Yes, but sir. If you are here, then moving here has an outcome here as 100. So which means it has a cumulative award of 100 into 0.9 from this state via this state. So this action right side has a greater value than 0. Are you agreeing? Let me again make it more smaller. Suppose this is goal and this action has a value. Let's say this value is 10. And I want to know what is the Q. Let's say this is S and this is T state. What is the QS right move? Right? What is the QS right move? Because my whole goal is to know this, then the optimal policy I can understand. How do I know this? Initial reward was 0. I move to this state, but this state has a reward to choose between 0 or 10. I will obviously choose the maximum 10. Now, what is the impact of that choice in this state? The impact is that if I can reach T, then 9 will be my reward, which can push T. Because it's a cumulative reward of gamma into 10. So this state will be updated.
So, sir, we will consider all the cumulative reward which will lead to the goal, right? The whole path.
No. That's what the learning thing is. Here, see, here you are considering for the value and iteration, you are considering every possible state to update. Here, what I will do, let me
Sir, I have a
again
question.
draw the diagram. What I will do, I will not, since the state space is huge, as you can understand, the state space is huge. You do not know which one will lead to the goal, right?
Yes, sir.
I will start in an arbitrary position. I will visit and update that. Next iteration, I will start in another arbitrary position. I will visit and update those. Next iteration, I will start in another arbitrary position. I will visit and update. Right? This has a very good convergence proof. If the convergence proof lies in this fact that if my action is deterministic, the assumptions are if your action is deterministic, the two, if the reward at each state is bounded by a constant value, and three, if your agent select action in such a way that you visit every state infinitely often visits, then by this way the learning will eventually converge into the value for every state for all S and A. It will converge towards the actual value SA. There is a proof for that. But now here you see that you might be wondering that it may be the case I do not explore a portion of the space. I do not bother, because if I could update and can converge by the set of examples that I have, that set of paths, I have guaranteed that I have found a path towards goal. I have found an optimal policy. That may not be globally optimal, but I have found a locally optimal policy. Agreed?
So, sir, we will consider the path which will give us the highest cumulative reward over there. Maybe.
Absolutely. So each time, so in a bigger grid, what we will do, let's say this is a very big grid. Suppose this is my goal. There, oh my God, I think it's just let me open it once again. Just excuse me for a minute. Yeah. Okay. So for a bigger grid, there may be obstacles inside it, also some path. So what I will do, see, initially everything is 0. I started with the Q function of everyone to be 0. Then randomly I choose a state and I keep on moving and updating it. See, if I reach a goal somewhere, obviously this state will be updated with some value, right? This state will be non-zero.
Yes, sir.
But if we move in this way, till we move this point, everyone will be 0 right now. Now, if you do it 1,000 number of times, it may so happen that you again go this way, maybe in a different path, then this state will update it with its Q value because this has already been updated.
Yes, sir.
Right? Now, in the third iteration, if you just go on doing like this, see now this state will be updated.
Oh,
Right?
okay.
Maybe in a fourth iteration, you go this way, only this state is updated. So if you give a sufficient amount of iterations, then this is bound to converge, and this is a theorem that it will converge based on these three conditions. And if you are interested to look at the convergence proof, you just go in the of Tom Mitchell's book. It is detailed proof is there. It's a theorem that this will converge.
Okay, sir. It is clear. It is clear.
Yeah. So what we finally did is that we somehow get a kind of our learned Q value or hypothesized Q value, which is basically the present reward, and gamma assumed hypothesized value function with that transition, which is basically we rewrote this function with respect to gamma into maximum of the A that we could select with respect to the Q value of where we go. I mean, this is A dash to make it more clear, right? So this way we iterate, right? And why we wrote this function this way? Because this is typically a dynamic programming paradigm as you are maximizing something. Did you get it? So this gives me the fact that my QSA in the formulation was RSA plus gamma of max A dash Q S dash A dash, where I through S, I mean delta S A will give me S dash to reach the transition. So when we are trying to iterate over this and try to finalize, we will converge with the values of this. And this is learning because you do not know the whole configurations. Neither you are trying to do it in a breadth first manner and trying to figure out every possible state values, which is infeasible in practice. This is the whole of Q learning is all about. Now I will finish off with a very small observation you might have noticed during this exploration of the path. It might be that if you have intermediate rewards in the state, suppose this state contain an intermediate reward R dash, this state contain an intermediate reward R dash. Consider the chess game. If you capture someone's queen, the reward should be more. You are in a better position, right, in terms of points. So that means sometime it may so happen that you go on collecting these rewards in such a way that you do not reach a goal at all, right? So it is the question of exploration versus exploitation in reinforcement learning. And it's a very pertinent question because how far you will explore new possibilities and how far you will exploit whatever you have learned for this is also to be considered, because otherwise what will happen in a grid, you might only visit in a biased way a set of state space which are in this space. Your goal may be here, you totally ignore this because intermediately you are collecting rewards in such a way that no action could push you into this boundary. Are you getting me what I am trying to address here?
Yes, sir.
Or no? See that when you will think of this action, I will think of this action in my algorithm when this action is maximum among all possible actions. Now consider this action has 100 and this action has 90. Whenever I reach this state, never I will consider to move this way. I will always consider to explore this way. That is the question of exploration versus exploitation. So what happens in those cases, instead of using QSA directly, we use a decay function, that if you explore this state often and often and often, your Q value cumulatively little bit reduce at every time, so that you do not get exploited by this path, you explore more paths. Agreed. See, here my exploration is with respect to maximizing the action which can result me to a new state. That is my exploration path. So I could get trapped into a set of paths and set of cells only, which is cumulatively enhancing my reward and reaching a fixed point or reaching a convergence point. However, maybe that this path will not reach a goal. Your goal is somewhere sitting in the other side, but you get so much cumulative rewards in between that you keep on switching into those. To eliminate and to make your exploration more towards the other sides of the gridway, you need to devise certain mechanisms. So one common sense, as I already pointed you many times what the common sense should indicate. The common sense is that I need not explore the same path again and again. So this exploitation of the bigger value would somehow reduce gradually when I infinitely going on and on with this same path, so that I could explore other possibilities. So in that case, we do not take QSA value as a start. We just initially we take more of that exploitation. Later we go on reducing the Q value so the new exploration can happen. Yes, Urvashi.
Sir, I'm saying, how will we reduce that? Like, you were saying we are occupied with those paths only because that is
Yeah, you
going.
will reduce. See, this is a value, right? Just consider the value that which is Q by K. So if K is 1, it is just this. If K is 1.01, that means I am gradually shifting, right? I'm not holding it anymore, right? Yes or no? If K is 2.01, then this is kind of 50. Now I will explore this path.
Yes, sir, yes, sir.
Okay, so sometimes this method is very much used because in chess and big games where the state space is humongous, see, ultimately you are trying to learn a final policy. In chess, it is, suppose someone plays this, I will play this, and you learn a policy. Now someone plays other way. Now you have a finite learning elements to explore and train your program. So the other way may not be known to you, and you are losing and losing the game. Right? That's why while learning, how do you go for alternative explorations? This is one of the mechanisms people follow. Am I able to make somewhat in a very naive sense what does the reinforcement learning and how to explore? Yeah.
And we will keep on updating this K value accordingly.
Yes,
Like,
what it happen? It happens in terms of epochs. So let's say first 100 epoch, I keep K as 1.
okay.
The next 100 epoch, I keep K as 1.2.
Okay.
Get it?
Okay, sir. So, okay.
So when I keep on increasing K over epochs, then after certain amount of training, I give the flexibility to explore more rather than always get exploited by the same path.
So ultimately, we will explore that whole grid and we'll
Yeah,
convert.
but that is not possible. That's why you have to stop somewhere.
Okay.
That's the one of the research area nowadays also, when to stop. Now see, have you seen the movie AlphaGo, by the way? I mean, if you have not, I mean, maybe after of the semester, because at the end of the semester, you didn't too much pressure. You please see the movie AlphaGo. It's a brilliant example of deep reinforcement learning, which is another advanced step from reinforcement learning, where not only you do reinforcement learning, but you also invoke a neural network to learn your policy. So just to give you an overview, what does it do? Instead of a policy learning, I am learning pi, right? It's a policy. Policy means it's a set of moves. Pi star is one move, one sequence of moves. What if I learn it as a neural network, this policy? This policy is nothing but an outcome of a neural network. When you fed me with such kind of an action, I will say you this based on the outcome of the neural network. That is a deep reinforcement learning. And AlphaGo is a game. Go is a game which is more complex than chess, and it has also a little bit of, I mean, very much higher number of variations. So DeepMind has produced a agent called AlphaGo, which can beat the 9Dan, the highest rated players in Go and world champions. Similarly, backgammon has also such kind of a neural network policy, which is a non-deterministic action outcome game, and it is also a brilliant example of reinforcement learning. Okay, so it's very fascinating to see that the environment that even if you do not explore, you can play there also. Think of a chess engine. You have not explored everything, but you can play depending on a Q value you have there in that state. Somewhere you have that Q value being populated there. So all this comes into a real life when you send something to Mars and all. See, in an environment which you do not know, but it's a control system or a reactive system which reacts from an environment. Something you do an action, taking back the environment feedback, you do next action. Some of your software and with the software and with the mechanism, the rovers goes into Mars and can land itself and can navigate and can do a lot of things. Isn't it fascinating? And one of the technique is reinforcement learning there also. Okay, so I'm a little bit ahead of time, so I will close here today. If you have any questions, you can ask. But this is the whole gamut of reinforcement learning I would like to introduce here, the third form of learning apart from supervised and unsupervised. The next class, I will continue with little bit more details where the action sequence may produce an uncertainty in the actions, the state that can be sensed. How does we do for the temporal, I mean, the learning if it is not for a temporal window kind of a reward we get, and a little bit of Monte Carlo policy evaluation to finish it off. So any questions?
Sir,
Yeah.
other than space missions like Mars mission, is it also used in simulation software like ANSYS, like in ANSYS we create a model and then based on different parameters, it gives performance values.
Absolutely.
For example,
I mean, I'm giving you a practical example where it is used. Stock market prediction, it is used because you cannot navigate the whole possibilities. You will not get immediate rewards because the stock market immediate rewards are not the visibility or the indication of the rewards in future or finally. So you invest in share, what is the stock market price goes ups and downs are your parameters. Based on that, you collect cumulative rewards and do a reinforcement learning. And you your investment in the share and in the stock market is the actions that you are doing. This is a reinforcement learning example. Driving car, driving a helicopter, automatically and flying a helicopter, cleaning a robot in its room and docking it in the energy window, playing football, robo soccer. Those who have an access earlier, MTech students do not have an access earlier here. Usually in the Gymkhana in KGP, there is a board where the robo soccer plays, and we have a very solid team of mechanical, electrical engineering students, computer science, who uses all these factors to play a soccer, football with the robots. All these are reinforcement learning because you do not know all possible moves. Scheduling, we use reinforcement learning. It's also used in scheduling and planning.
Sir.
Yes.
With the constant grid space problem, like anything, if we run this, then it will give us the same as a dynamic programming, right?
It
like
is dynamic programming. See, whenever you need to have certain options to choose the maximization or an optimization to go with it, it's a dynamic programming, obviously.
Yeah.
It is. I mean, if you implement this, you will see the point where you need to select this maximization and maximization factors are your dynamic programming points.
Yeah, it is, as we are using the recursive thing over here.
Yeah. But I hope I can make you understand where does the learning comes here rather than state space exploration. That's the main difference of reinforcement learning, because everywhere this question comes in your interviews and all. I mean, what's the difference of state space exploration versus reinforcement learning? If I give you the state space, you can explore, but if I don't give you the state space, you have to learn. And the analogy comes from the fact, how do we do in the maximum likelihood estimation? We just count and learn a probabilistic estimate. Here also we learn an estimate of the Q function through which we dictate a policy.
Yes, sir.
Okay, we will see more variants and ramifications of this in the next class. Okay, so I am stopping the sharing and stopping the recording.